Hi, my name is Franz Machado, and today I'm going to present my project, Experimental and Simulation Study of Cosmic Muons Detected with a Water Cherenkov Detector of the LAGO collaboration. In the present work, we study the secondary particles produced by the interaction of cosmic rays in the atmosphere. We use real data from a detector located in Chitaga, Colombia, that is part of the array of the LAGO collaboration. One of the main goals of this work is to replicate known results about the muon, but by using a different method of analysis. The second main purpose is to estimate and compare the simulated known results about the muon. Well, the first part is, in the first part we use real data. So with that data, we can obtain two principal histograms, the charge histogram and the histogram of temporal differences. The charge histogram is mainly used to calibrate a detector because we can find the relation between this unit, this is the unit that the electronic use to save the data, and the energy. For that we use the muon peak that is mainly known. And the histogram of temporal differences is used to calculate the mean lifetime of the muon. Well, in this part, we fit the curve. In this case, we obtain the relation between ADC and energy. In this case, 350 ADC is equal to 180 MEPS. And for this, we found that the mean lifetime of the muon is this value, 2.226 plus minus 0.01 microseconds. That it's very close to the most accepted experimental value. Well, then I developed a program in Python to select the electron and positrons associated with the muon decay and find this histogram. This is a Mitchell electron spectrum. Well, the next part is simulation. In this part, we simulate a detector of 60 centimeters of height. And we found that the histogram of the distance traveled by the muon inside the detector for all the muons has a peak that is dominated by the vertical muons. In this case, this is the histogram for only vertical muons. So we can see that the histogram for all muons is dominated for vertical muons. In the next slide, we can see that vertical muons, that blue histogram, dominate the number of photoelectrons associated with the muon, in this case. For example, the red histogram is the number of photoelectrons associated for all muons, while the blue histogram is only associated with vertical muons. So we can see that the peak is almost the same. So we can say that this peak is mainly because the vertical muons. So again, we can adjust this curve and we find a relation between the number of photoelectrons and the energy. Well, in this slide, we compare the energy histogram or the energy spectrum. In this case, this is the simulated energy spectrum. This is the energy spectrum using the real data. In this case, we are using data from a detector located in Antarctic. So in this case, this peak is much wider than in this case. This could be because an error in the amplification factor. So we will redo this energy histogram. In the next slide, we can compare the Mitchell electron spectrum. The red histogram is a Mitchell electron spectrum using an energy distribution that was studied by Mitchell, while the orange histogram is the Mitchell electron spectrum using real data. We can see this difference here because as we are using a a secondary trigger, we are discarding low energy muons. So it's for that reason that we don't have too many events in this part. But the peak is almost the same, so this is in a good agreement. That's all. Thanks.